Hey guys, and welcome back. My name is MrCaproni, and I teach AP Stats at Western Hills University High School for CPS. If you're joining us today, we are jumping into the second type of testing for hypothesis testing. We've been doing quite a few videos on hypothesis testing over the last few weeks, so if you have missed any of those and you want to catch up to where we are right now, you can always check out my YouTube channel at MrCaproni. No space, no period, so you can see all the past videos and all the future videos there. So if you feel like you're left behind and don't really know what's going on, check out those videos first because they're a great place to start. But if you've been with us along the way, then you guys are ready to get started. We're launching into a new chapter. We're going to be looking at two proportion hypothesis testing today, where we have been doing one proportion hypothesis testing in the past. So this will be our second type. We still have quite a few more types to cover, but as you'll see, these will go through much quicker because we did create a 7-step process that we're going to use for hypothesis testing. And we're going to use that same 7-step process today. There are going to be a few differences, but for the most part, a hypothesis test is a hypothesis test. So I hope you guys learned something new today, and thanks for joining me for AP Stats Day 20. So let's start by looking at this example. It says a textbook sales rep comes in and claims that AP students only pass the graduation test 10% more often than a non-AP student. So MrCaproni, myself, seems annoyed by this because I'm like, there's no way. My AP students are far better than just 10% more often than a non-AP student. I think it's going to be much, much higher than that. So I go out and get a sample. Now here's the problem is I need to get a sample of both AP students and non-AP students so I can see if the difference between the two of them is actually 10% or more. So I go ahead and I get a random sample of 200 students. Some of them are AP, some of them are non-AP. And I look through the data for my AP students and find out that 92% pass the graduation test and find out that only 75% pass the graduation test out of my non-AP students. So I'm in a dilemma because that's a 17% difference, not a 10% difference, which means is 17% a high enough difference from the 10% that I can claim the 10% is a false statement, and we can move to accept that it is actually higher than that. In particular, in this case, I got 17%. So this is a hypothesis test situation. But here's the difference. Before, we had a given statement about our proportion, and then we had a sample to test that proportion. But in this case, we're looking actually at two different samples. We're looking at a group of AP students and a group of non-AP students. Now, when I look at each sample individually, they're going to have different statistics with them. For example, my AP students may have a much higher center, a much higher average or mean, median, mode, whatever, but it may be much more spread out. Maybe there's going to be some students who shouldn't have been in an AP class to start with, and they're actually way down low. So their standard deviation or IQR is much wider. Whereas with the non-AP students, they may have a lower center, but it's possible that they're not as spread out. Or maybe they are, I'm not sure. But what it comes down to is when we're looking at the AP students versus the non-AP students, they are not the same samples. They will have different statistics, which means we can't just use a one proportion sample test for this. So we can't do the one proportion z-test. We need something else. So there is a specific test that we can use for when we're still dealing with proportions, but when we're trying to compare two different samples together to give us our number in question. In this case, the 10% is only one number, but it is describing a situation of two different groups. And in fact, it's the difference between them. This is where we're going to launch in today to start learning what a two proportion z-test looks like. So let's start off by looking at some of the differences and similarities between proportion z-test and the two proportion z-test. Now, there are two major inference topics that we covered. One was creating a confidence interval where we said, hey, we believe the true value to be between this and this. And the second was the actual hypothesis test where we had a statement and then we tried to test if it was true. So we're going to take a look-see at both of those because just like with hypothesis test, you can do a confidence interval for all the different types of tests as well. So you'll see we'll change a few things and then everything else will be the exact same. So we'll look at those two items, confidence intervals and hypothesis testing, but through the lens of a two proportion test instead of a one. So first off, two proportion tests are much more common in the real world because they're far more interesting. A lot of people don't want to just say, hey, that statement was made. I want to test if it's true or not. A lot of people would rather like test two different groups and see how the difference between the two are. Anytime you run an experiment, a lot of times you're going to have a control group and a group that you actually made a change for. And the whole point is to prove that your change was effective in some way. So a lot of times you'll be comparing two groups, in that case, a control to the experiment group, so that you can get a final result on if you were effective, which makes this one a lot more common than some basic one that just has one proportion in it, because that would just be one claim. Now, one of the major differences with this is the standard deviation, all right? So if you remember, our original standard deviation when we were dealing with the one proportion was the square root of p times q divided by n. Now, if you remember, back in the day, we went through this whole, what happens when you take one standard deviation of a sample plus another standard deviation? How do you combine them? And we said you can't just add the two standard deviations together. What you have to do is switch them to be a variance first. And remember, you switch them to be a variance by squaring each one. So if we had the square root of pq over n plus the square root of pq over n, but this was for my sample one and this was for my sample two, then what we would do then is first switch them into variances, which means you have to square each one individually. So that would just basically take away the square root. And then you add them together, and then to switch back into standard deviation, you have to square root the whole thing. So this is actually just an application of that rule we used to go through. And you'll notice that in a lot of these formulas where we have the standard deviation or the standard error, we actually use a sub 1 and a sub 2. What those little tiny numbers down below tell us is that these are the statistics and pieces of information from our one sample, whichever we name that to be. So maybe from our example before, we say one is AP students and two is non-AP students. Then anywhere you see a little sub one means that this was data or information that came from the AP students. Anywhere you see a two, that means that those are the statistics and data that came from the non-AP students. So when you see the little sub one, sub two, that's all that means. Now, none of this should be surprising because we're using a concept from earlier in the year of how you combine two standard deviations, and we just create a new standard deviation about the difference between the two. Now, why do we subtract? Because the whole point here is that we're trying to find what the difference between the two groups are. So if you want to know the difference between the two groups, then you're just going to take all of the information about the one minus the information about the other. And that's where this whole subtraction comes in. So when we're doing a two proportion test, we still only use one standard deviation, and you'll find out in a little bit, one mean. We just combine the two together to create one formula. Now, what's the great news? Do you have to memorize these formulas? Absolutely not. We're going to do all this work on our calculator. You guys have already seen the menu where it has all the different tests on there. So we're going to be able to just plug our information in, and it's going to do all of these formulas for us. We just have to remember that this is called a two proportion z-test. All right, so let's keep moving along. Along with our one proportion z-test, we had assumptions and conditions that had to be met. A lot of these are going to be the same, but because we have two samples now, they're slightly different. But these same assumptions and conditions apply for both confidence intervals and hypothesis tests. It's the same for both. So if we look through here, what are the conditions that must be met? Number one, randomization condition. We already know this. It means that each one of our samples must be independent of each other, and they should be randomly drawn in some way. A lot of times they straight up just say that in the question. Next, the 10% condition. We know this one already as well. This is where you say, hey, 10% or less of your sample size must be 10% or less of the whole population. Then we have our independent groups assumption. This is actually the new one. Because there are two different groups, one of the things we have to make sure is that one group is independent of the other. In other words, if the data that's produced from the AP students comes out that shouldn't change the results for my non-AP students. In that case, it's pretty easy to tell that one shouldn't affect the other. But in some cases, it's not so cut and dry. Sometimes when one happens, it can change the results of the other. In that case, it would fail the independent group assumption. Next off, another one that we're used to is the success fail condition. This is where you have to take the sample size multiplied by the probability of success and the probability of failure, and both of those must be 10 or larger. Cool? Now, with that said, we already have the whole central limit theorem that helps us say, all right, when we deal with this information, we know that when we draw samples, it will create a normal curve approximately. That rule actually applies here as well because that rule will work for each sample individually. And when I combine two normal curves together, it's going to create a single normal curve with its difference. Now, what will be different with this normal curve? Well, we already talked a bit about the standard deviation and how that's going to change. But what about the mean? Well, the mean actually is just going to be the difference between the two proportions. So when we were dealing with one proportion z-test, we just said that the mean was equal to whatever the proportion was in our original statement. Well, in this case, it's very similar because we're comparing two and we're seeing what the difference between them are. The mean that we're going to use is just going to be the first sample's proportion minus the second sample's proportion for the exact same reason that we did that with standard deviation. So this shouldn't be surprising, but this is going to be the major difference between the two. So when we're looking at a two proportion test, our mean and standard deviation is no longer what we used for the one proportion test, where it was just PO and just one of these guys by themselves. When we do a two proportion test, it's now going to be the difference between two samples and this whole thing for the standard deviation. So when we're doing the confidence intervals, if you remember, confidence intervals was just whatever the mean was, plus or minus our critical value times the standard error. We already know all of these things because they're the exact same. We just said what this guy is. It's just P1 minus P2. And the Z star isn't going to change. It's still going to be like the 1.96 for the 95% and so forth. So those numbers won't change. And the standard error is just following this formula. So let's go ahead and look at an example of finding a confidence interval for a two proportion test. I'm not going to apply all of this using the formulas. Instead, I'm just going to use our calculator function that we already know how to do. But when we go into our calculator menu, we're going to choose the two proportion option instead of the one proportion. So let's go ahead and quickly run through a confidence interval example question for this material. So it says here, researchers at the National Cancer Institute released the results of a study that investigated the effects of weed-killing herbicides on house pets. They examined 827 dogs from the homes where herbicide was used on a regular basis, diagnosing a malignant lymphoma in 473 of those. And then of 130 dogs where there were no herbicides used, 19 have the same lymphoma. So construct a 95% confidence interval for the difference between these two. Now, here's the deal with this. Why is this a two sample confidence interval instead of a one proportion? It's because we have two samples here. One, where the herbicide is being used, and we're seeing how many dogs got sick with the herbicide. The second is when no herbicides were used in the household, and we're looking for that same lymphoma to see if the difference between them exists. Because if there's a higher chance of getting lymphoma when you're using the herbicides, obviously they're going to have to release that, hey, don't use this with pets because it could kill them. So they're seeing if there's a difference between the two. In other words, when you subtract the one proportion from the other, am I going to get an answer larger than zero? So because if they were the same, the difference between the two should be zero. Now, constructing a 95% confidence interval. What type of stuff did they give us? Let's write out our data first. We have our number of successes for the first group was 473. It may seem dark that we're calling successes when they get lymphoma, but remember, we're just running a test here, so it's not actually a success in life. Then we have the total sample size for that first one was 827. And then the sample number of successes for the second one was 19, and that was out of a sample size of 130. So let's go ahead and plug that into our calculator. So as always, I'm using the TI Inspire for our class. If you want to use a different calculator, that's perfectly fine. Just Google how yours does confidence intervals. So if I want to do a confidence interval, remember we go to menu, we go down to our statistics, and in there we have both our confidence interval and our hypothesis test. In this case, we're doing a confidence interval. We've already done the 1 proportion z interval, but in this case, we're moving on to our new one, the 2 proportion z interval. So if I click on that, what's it asking for? It's asking for our number of successes for the first one, total sample size, number of successes for the second one, total sample size, which is actually conveniently all the data I just wrote down. So let's go ahead and look back at our snapshot of this. We have 473 out of 827. So 473 out of 827. And for our second sample, we had 19 out of 130. So 19 out of 130. We did want to go ahead and do a 95% confidence, so we're going to leave this as 0.95 and go ahead and hit OK. Whoa. Now look, it seems like there's a lot more here than usual, but that's because we had 2 samples. So notice it gives us the probability of success for our first sample and the probability of success for our second sample. So if you wanted to do the math, remember that's just your number of successes divided by your total number in the sample. Out of the ones who used the herbicide, 57% of those dogs ended up getting the lymphoma, whereas only 14% of the dogs that didn't have the herbicide got it. So there is a pretty large difference. How large is that difference? Well, remember, when we're trying to produce a difference, we start off with the difference between those two, which was 42.5793. And then we go to the left and right a certain number of standard errors. In this case, because we're doing a 95% confidence interval, we go 1.96 standard errors in either direction. So that gives us these two numbers right here, the 0.356332 and the 0.495254. So what does this mean? It means that if I were to go out and grab any given sample of herbicide-used dogs and not herbicide-used dogs, I would expect the difference in the percent of them that got lymphoma to be somewhere between 35% and 49%. If I rounded that properly, I would say probably somewhere between 35.6% to 49.5%. All right. So that would be our final answer for this question, which I believe I go ahead and have on the next slide right here. Remember, this is a common way to write out your confidence intervals. You could also write it by putting that, hey, we wanted to do the first proportion minus the sample proportion for the second one, and we believe that to be between these two numbers. So you could write it out that way as well. Either way of writing out your answer is correct, but remember, what would this mean in words? It means that we believe the difference between herbicides used dogs that got lymphoma and non-herbicide used dogs that got lymphoma would be somewhere between 35% and 0.6 and 49.5%, which is a huge difference between the two populations. So it's going to be pretty safe to say later on that this herbicide is causing lymphoma for these dogs. Now that we've knocked out confidence intervals, let's talk about hypothesis testing. Now, a lot of this is going to go the same way, but you're going to find out that there's a term that we use in hypothesis testing when we have 2 samples called pooling the data. Now, what does it mean to pool it? Well, it means that a lot of times when we do a hypothesis test, we're not trying to prove that the difference is larger or smaller than a number. We're trying to show if there's a difference or not. So when I talked about before, when we have an example of like an experiment, you have your control group and your experiment group, and you want to see if the data has a difference between the two so you can show if your thing was effective or not. So we don't usually compare it to a given number. Instead, we just want to see if the difference is higher or lower to 0. Or just like with the last one, we have our third one of we don't care if it's higher or lower, we just care that it's different. So there are, again, three types of null hypotheses we usually, sorry, null hypothesis, we have one, there's three types of alternatives. So usually when we write out a null hypothesis for this, there are two ways to write it, and we'll talk about that in a little bit. But because we assume, starting off, that the null hypothesis says there is no difference, meaning that the difference between those is zero, then that means that if there's no difference between the two samples, they should have the same standard deviation, the same mean, the same everything. So we don't have to worry about that whole two sample difference thing because we're assuming that they are the same. So we're able to pull the data together to do one test for it. So it goes through here some of the formulas that we would use for this. But again, it's not always super important for us to memorize all of this stuff, because although we have a new standard error, notice it's still pretty much the exact same. The only difference is they use the same numbers up here for both, but notice it still has the sample size from the first one, sample size of the second one. The rest of the formula is the same. And again, all of these will be found on your formula sheet when you're able to take the AP test. Now, we'll reject our null hypothesis just like before if the difference between the two proportions is large enough that we believe the p-value will be extremely small. So we're going to do the same thing we did with our last hypothesis, where we're going to plug in all of our data into the calculator. It's going to give us a p-value. If the p-value is less than our alpha, or level of significance, then we will be able to reject the null hypothesis. If the p-value is greater than our level of significance, or alpha, then we will fail to reject the null hypothesis. Okay, so it works the exact same way as before. We're not really doing anything different. Now, with this, it has a few other things. We go through the conditions for the two proportions, but they're the same for the confidence interval that we already discussed. And here's where I said we'll talk about more on how you can write your null or alternative. So the default that we usually write on paper is this, is that if you find the difference between the first proportion and the second one, if there is no change, then that should be equal to zero. But what would we write for the alternative? So for the alternative, one of three things can be true. Either P1 minus P2, that's a minus sign right there, is going to be bigger than zero. So that's where we think that the difference between those does exist and it's going to be bigger than zero. It is possible that it could be less than zero, or it is possible that it's just flat out not equal to zero. And the wording of the question is what's going to tell us that. It is going to say either something along the lines of, hey, we believe that the first sample thing is going to be higher than the second one, or we believe it's going to be less than the other one, or we believe that it's not the same as the other one. Those would be the appropriate kind of phrasing for those three symbols for our HA. So when we're looking through this, don't freak out. It's almost the exact same as before. Now, the only thing you have to be careful of is when we plug it in the calculator, it usually looks more like this. Instead of saying P1 minus P2 is greater than zero, what they do is a little bit of algebra and just move the P2 to the other side. Now, basic algebra tells us that if we are subtracting, then we have to add it to the other side. So really, this whole phrase just becomes this: P1 equals P2. If we're looking at this one, it would become P1 is greater than P2. For this one, it would become P1 is less than P2. And for this one, it would be P1 is not equal to P2. So those are kind of our set HAs that we would use for our two proportion Z test. Now, again, we have our Z scores that we have our standard error. None of this is really different than what we said before, other than the fact that since we're pooling it, we can just use the same P and Q up top. And then we're ready to do an example. Now, although we are going to go a little bit longer than usual, I don't want to rush through this example because I want you to see all 7 steps of the hypothesis that we're going to do for it so that we can clearly define some of the differences that we see here from the one proportion Z-test. Now, going through this, it says a Vermont study published by the American Academy of Pediatrics examined parental influence on teenagers' decisions to smoke. A group of students who had never smoked were questioned about their parents' attitudes toward smoking. These students were questioned again 2 years later to see if they had started smoking. The researcher found that Amongst 284 students who indicated their parents disapprove of kids smoking, 54 became established smokers. Among the 41 students who initially said their parents were lenient about smoking, in other words, they didn't really care if they smoked or not, 11 of those students became smokers. These data provide strong evidence that parental attitude influences teenager decisions about smoking. So here's the deal of what's going on. They are saying, hey, we want to know if parents saying they care about their kid smoking or not changes whether or not the kid actually smokes later on. So they went through and actually found two groups. Now, the two groups here are the students whose parents said, no, you shouldn't smoke, and the group of students whose parents said, I mean, you do you, man. So those are our two groups. And initially, none of the students smoked. But after 2 years, they went back and asked, hey, have any of you started smoking? And that's what we're going to label as a success, is how many of those students started smoking. So let's go through our steps here. First off, what type of test is this? We are going to say that this is our two proportion z-test. All right, so nothing fancy there. That's just the name of this one. And the reason we're choosing two proportion is because obviously we're looking at number of successes and total sample size for two different groups. We're looking at the parents who disapproved and the parents who didn't care. So we're looking at those two groups, which means we can't just do a one proportion z-test, we have to do two. We know it's a proportion and not like a quantitative mean and standard deviation type question, because it gives us a number of successes and a total number in the sample. So that always kind of is setting us up for the proportion of success type question. Now, since we have defined our two proportion z-test, our other step was to check the conditions. I said this is the one that a lot of times people forget. So let's go through. It says, first off, random. Was this random? Well, did it say in here that they randomly selected students anywhere? Let's see, publish, blah, blah, blah. These were questioned again. It actually doesn't say how they chose the students. It just says a group of students who were never smoked were questioned. So we actually don't know if this is true or not. So I'm going to put a little question mark there. And if you remember, we have said there's a given statement you always give when this is the case. We don't know if it's random or not, so we're going to go ahead and proceed with caution. So remember, you would just write that out. You would say, we're not sure, so we will proceed with caution. Now, let's check out our other ones. 10%. Is 284 and 41 students going to be more than 10% of all students? Heck no. So that one's a very easy, yeah, we did this, it's less than 10% of the population. Independent groups. Do I think that my group of students whose parents disapproved are going to change the outcomes of the other students? Well, I mean, any more than normal peer pressure, I'd say no. So we're probably safe here. One group shouldn't change the outcome of the other group. If they started, that doesn't mean they will. It just depends. All right. So all of that is just normal error of a student being a student. Success fail. Now, for success fail, it is slightly different for a two proportion test than it is for a one proportion test. Because we don't have an initial proportion to multiply our sample sizes by, instead they kind of change this rule slightly to just say that the number of successes you have must be greater than 10. So in this case, the number of successes for parents who disapproved was 54, and the ones whose parents didn't care, the number of successes were 11. So both of those cases, we actually have above 10. All right. And for the failures, they would both also be above 10, because actually a lower percent of them started smoking than didn't. So all four of those are going to be greater than 10. Remember, why did I say four of them? Because we would have number of success for the disapproving parents has to be bigger than 10. It was 54. Out of the 284, the rest of them didn't start smoking. That number is obviously going to be above 10 as well. For the parents who didn't care, same thing. Number of successes was 11, but that wasn't majority of them. So the number of people who didn't start smoking is also above 10. So we can say that that is a check, meets all of the things. So let's go ahead and start writing out the information that they gave us. So in this case, we're given essentially four different things to look at. We are given two samples, and we are given the number of successes and the total number in each of those samples. So in this case, we're going to go ahead and write that out. And for our disapproving parents, which I'm just going to call D for right now, we're going to label them as our first sample. And 54 of them started smoking after, out of the 284. All right. And of the second one, we had 11 out of the 41. Now, that's all the information that was given to us. So let's make sure we have a solid null hypothesis and alternative hypothesis. So HO, we said that one's always pretty standard. There's the two ways to write it. We're going to say that either P1 minus P2 is equal to 0. Or a second way we could write it for our calculator friendly version is by moving that P2 to the other side to say that P1 then is obviously equal to P2. So you could write this either way. And then our HA in this case, we have to check, did it give any indication that one should be higher than the other? It says, do these data provide strong evidence that parental attitude influences teenagers' decisions about smoking? So in other words, would their attitude raise the chance or lower the chance that it's smoking? It does not say more or less. It just says influences. So in this case, I think we are in a prime situation to use our not equal to symbol. It does not indicate that we think they will be better or worse. We just know that it's going to be not equal to 0. So I'm going to do P1 is not equal to P2. Now, from this point, we have named our test, we've checked our proportions, we've checked our conditions, we've written everything out that we have, and we went ahead and wrote our null and alternative hypotheses. All right, so now we can go ahead and move on to plugging this information into our calculator. The only thing we're missing is our alpha. Now, we do want to define the alpha before we plug in our calculator so we're not swayed in our opinion of picking one. In the actual question, it did not give us a level of significance, our alpha. So we just pick one. We said usually if they don't give us one, we default to just saying that it should be 0.05 for 5%. So that's going to be our level of significance. If our p-value ends up being smaller than that, we're going to reject the null and accept that they are indeed not equal, which means parents do influence the decision. If the p-value ends up being larger than alpha, then we're going to say there's not enough evidence to reject this. So really, parents make no difference whether kids end up smoking or not. All right. So let's go ahead and plug all of this information into our calculator. So we're going to go to menu again. There's our confidence interval stuff still in there. In this case, we're running the stats test, but same thing. We had one proportion last time. We're looking at our two proportion this time. And just like before, it's going to ask us for very similar data. It's going to ask us for our number of successes for the first sample, which was 54, 284 for the total number in that sample, 11 successes for our second sample, and 41. And it actually defaults to having it as the not equal to. But notice the greater than or less than are also there. But we are using the not equal to, so we will move forward with that. And it tells us that the p-value for this is 24.2215% or 0.242215. So that means that in our first sample, it was less than the second sample. All right, so you can see here, 19% of students whose parents disapproved ended up smoking, whereas 26% of parents who approved started smoking, or sorry, not approved, but didn't care one way or the other, started smoking. So the proportion for our second group was quite a bit higher, from 19 to 26. But here's the deal, is our sample size was so small for that second group, 41, which means it probably had a pretty high standard error. So when you look through the formula, it still gave us a pretty high p-value of 0.24, which is almost 1/4 of the time that this sample could occur given our situation. So if we wanted to make this a little bit lower of a p-value or increase this study, the best way to improve it probably would be to raise the sample size of that second group. A sample size of 41 just isn't that large, and it's probably the reason why we're going to end up failing to reject. So again, what's the p-value we got? We got 0.242215. So I go ahead and go back. Point two, what was that again? 0.242215. That is our p-val. And that is obviously larger than our alpha. So what does that mean at the end of the day? Well, if I were to answer this question, we would say that there is not enough evidence for us to reject our null hypothesis that there is no difference between these two groups, which means at the end of the day, we would have to say that there's not enough evidence for us to say that a parent's opinion changes the decision of their child to smoke or not. So that's going to wrap up this entire example. We went through all of our steps, kind of knocked them all out. I know it took a little bit of time, but this is the two proportion z-test. As always, I'm going to provide more examples for my students. I would suggest you check into your textbook or look online for other examples of two proportion z-tests. This was just one, but for the most part, they're all going to follow the same process. After we go through quite a bit of these tests that we'll go through, because we'll move on to a new one in the next video, I'm going to make a sheet that will go through all the different types of z-tests that we cover and t-tests that we cover. We'll get to those. And you'll see that the major difference between the two proportions and one proportion is this whole idea of changing our HO and HA. So if you're understanding this, then great, because you're in awesome shape to knock out the rest of these. All right, so with that said, let's end this video. Hey guys, thanks for joining me today. I hope you learned something new. Remember, we went through the two proportion z-test today. We've already covered the one proportion z-test in other videos. Remember, if you ever get lost or confused or forget things from the past, you can always check out my YouTube channel at MrCaproni, no space, no period, and you can look through all of those videos that we've gone through already. I'll be releasing a few other examples of the content we covered today. Remember, we looked at confidence intervals for them, and we also looked at hypothesis testing for the two proportions. So, I hope this was helpful, and as always, guys, stay fit, stay healthy, and have a wonderful day.